I would like to first thank the organizers for giving me the opportunity to speak here. It's a pleasure. And yes, so I would like to talk today about higher Lie theory in positive characteristic. And so, well, so what I want to explain is that I think there is an intersection between different subjects where Lie algebras appear that one can call higher Lie theory. And so my first goal will be to explain or give an overview of what that might be in characteristic 0. And then my goal will be to explain how one can generalize this to a positive characteristic setting. So, okay. Let me first start by asking what are Lie algebras good for. So, yeah, okay, so if you want to stay, so if you want to be correct, you should say for many, many things. And among these many things, I want to somehow explain a few of them. So, I mean, we saw, for instance, Lie algebras and infinity algebras in Chiara's talk, which appear, and in other talks. So, the subjects that I want to talk about, where Lie algebras appear in different manners, are the following. So, they appear in deformation theory. They also appear, I mean, this is a bit tautological, but in Lie theory. And by that, I mean classical Lie theory. And then the third subject will be in rational homotopy theory. Okay. So, let me first start by, well, fixing a field, and it's going to be of characteristic 0. And let me explain what I mean first by deformation theory. So here what I will mean by deformation theory is infinitesimal deformations. So roughly, what I want to consider is the following. So point A, let A be some type of object, and then P a type of structure. You may ask yourself, what are the structures of type P that I can put on A? And well, the heuristics is the following. You could imagine having some space, which would be the moduli space of structures of type P in A, and where your points would be given by structures, and then there would be some geometrical structure on the whole moduli space. And so infinitesimal deformations in this picture, they correspond to the following. I pick a structure, so a point in my space, and the infinitesimal deformations will be given by the infinitesimal neighborhood of my point inside this moduli space. Now, what happens is that this moduli space might not exist in general. There is no reason. But you can keep this heuristic and actually formalize this geometrical situation via the notion of a formal moduli problem. So I don't want to get into the details of what formal moduli problems are. I'll just want to state the following theorem given these heuristics. So this theorem, there's a theorem by Lurie and Pridham that states that once you have this definition of what a formal moduli problem is, you can construct an equivalence of infinity categories, or homotopy categories if you prefer, between these Forma moduli problems, which are a homotopical notion, and differential graded Lie algebras localized at quasi-isomorphisms. So we have Lie algebras that appear. And now, something that I want to point out is that, well, how do these Lie algebras appear in this context? Well, the functor here, you can think of it as a tangent functor. And it happens that these objects have a well-defined notion of a tangent complex. And this functor essentially says that I put a differential graded Lie algebra structure on the tangent object. On the other, so this is a bit reminiscent of how Lie algebras first appear as, well, taking the tangent at the unit of a Lie group. But let's keep that. I don't want to make this analogy precise. Now, what I want to ask is, what is this other functor? So in general, it's a bit subtle to construct, but I want to give the idea behind this functor, and the idea is the following. So given a differential graded Lie algebra, G now, well, what this other functor should give you in some sense is what people have often called the deformation infinity groupoid associated to G. And what is that infinity groupoid? Well, you can think of it as some kind of space again. And here the analogy is a little bit the same. So points in this space now correspond to infinitesimal deformations of your original structure. And then paths between these infinitesimal deformations correspond to equivalences between those deformations, and so on and so forth. Okay? And so this is an heuristic. But now what I want to talk about is, well, these infinity groupoids, you can actually present them at a point set level by simplicial sets which are count complex. I'll keep referring to them as infinity groupoids and not count complexes to keep the analogy with classical Lie theory, where if you integrate a Lie algebra, you get a group. Here, you can think of infinity groupoids as an opto homotopy version of a group. I think this is a nice way to think about them. I'll make that a little bit more precise after. But so let me just write what I said. So what I mean by integration theory here in this particular context will be to construct a functor, and this is at the point set level, from Lie algebras, or say L infinity algebras, which I'll come back to them a little bit later, to these infinity groupoids, and give an algebraic description of this object. So this is what one can refer to as integration theory, okay? And so it was already mentioned in the previous talk, well, and I'm sure many of you are aware that you have, in a Lie algebra, you have the Moore-Cartan equation. So G be a DGLA. So an element in degree -1 is a Moore-Cartan if it satisfies the following equation. So the differential of alpha plus 1/2 of the bracket of alpha with itself is equal to 0. And it's a known heuristic that points in that space should correspond to solutions to the Moore-Cartan equation in your differential graded Lie algebra. But then, okay, so we have a set, the Moore-Cartan set. Now the question is how to enhance that set into a full simplicial set, which is furthermore a count complex. And so, oh, I can't push this further. So there was a first construction of such a functor by Inich, which, well, it gave the right homotopy type of this space, but algebraically, you could argue it was a little bit too big. And so later on, Kessler gave a refinement of this construction, which had the same homotopy type as before, but algebraically was smaller. So smaller refined construction. And so, well, these two spaces have the same homotopy type, but algebraically they don't behave in the same way. And so, using this Kessler functor, what I want is to connect this deformation story to classical Lie theory. So, yeah, I'll continue here. Okay, so how does this connect to Lie theory? Well, it's quite known that if I have G a nilpotent Lie algebra, and here it's not graded, it's not differential, I just mean a classical nilpotent Lie algebra, I can cook up a group from it called the exponential group of G. And so what do? Well, I keep the same underlying vector space of G, so as a set, and now I endow it with a group structure given by what's called the Baker-Campbell-Hausdorff formula. And so this formula, let me point out that this formula is an infinite sum of the following terms. So you take the sum, and then you need to add brackets of x and y. And then you get first a bracket of them, and then bracket, iterated brackets. Well, and then it runs forever. And since you want to give an algebraic meaning to such a formula, that's why this nilpotent hypothesis appears at the Lie algebra level. Now, let me finish this section with the following theorem. By Getzler. So now if R is Getzler functor, and if I apply it to such an nilpotent Lie algebra, what do I get? I get the nerve of B of the exponential group. And what I want to point out is that this is not a homotopy equivalence. Well, not only, it's an isomorphism. So on the algebraic level, using this construction of the integration functor, you do recover a classical construction from Lie theory. So this is an iso. And so okay. And so now let me state another theorem. So the idea is, well, this is what happens when you have a differential graded Lie, well, you have a nilpotent Lie algebra. You apply this integration functor and you recover this classical construction, but in fact, this admits a generalization where, so as I said, you have an infinity groupoid, so it's a Kan complex, but it's not only a Kan complex defined in terms of a property, so there exist Horn fillers. In fact, these Horn fillers are given by explicit formulas, and these explicit formulas, you can think of them as higher Baker-Campbell-Hausdorff formulas. And so let me state this theorem. So here is Kessler functor, but presented via operatic calculus methods. So the image is an algebraic Can complex, meaning the horn fillers are given, and you can think of horn fillers as higher Baker-Campbell-Hausdorff formulas. And if I take the 2-1 horn, and I fill it in the context of an nilpotent Lie algebra, I do get back the original Baker-Campbell-Hausdorff formula. So it does generalize this. So, okay, now we have our integration functor. You might say that we are quite happy, but we can even be happier about all of this. So, okay, no, this is the one, okay. Yeah, and this is number 2. Okay. Okay. And then. So now what I want to talk about is how this relates to rational homotopy theory. And the way it relates to rational homotopy theory is the following. So we have a functor from these differential graded Lie algebras or infinity algebras to infinity groupoids, and it happens to admit a left adjoint, and it's this left adjoint who will give rational models for spaces. And these rational models for spaces, you can think of them as some kind of simplification of the original constructions by Quillen in rational homotopy theory. So let me mention this, rational homotopy theory. So let me say that these constructions, so in the case of differential graded Lie algebras, they are due to Buig, Felix, Murillo, and Tonre. And then in the case of L-infinity algebras, to Robert, Nico, and Valette. So in fact, what you get is an adjunction where on the right you have the integration functor. So let me write it like this. And turns out that L gives rational models for, say, pointed nilpotent finite type spaces. So all these three things, they are interrelated, and I guess that's what one may call higher Lie theory. And now what I want to explain as a final thing in characteristic 0 is that, well, I want to point out that here in the Baker-Campbell-Hausdorff formula, this formula happens to be infinite. And furthermore, if you look at the Moore-Cartan equation for an L-infinity algebra, it's also given in terms of an infinite sum. And so there is somehow another approach that you can take using a version of these algebraic structures, which I call the absolute version of these algebraic structures, that makes any infinite sum of operations well defined by definition. So let me explain that a little bit and explain also how you can redo this story in this framework of absolute algebra. So the absolute story. Okay, so let me recall that an L-infinity algebra, it's given by a collection of symmetric operations for n bigger or equal to 2 on a chain complex G. They satisfy some relations that you can think of them as, well, the bracket is not Jacobi, but it's Jacobi up to L3, so on and so forth. And now let me point out that there is an equivalent description of this algebras as algebras over the following monad, so the monad associated to the L infinity operad. And so let me just point out along the way that, well, this structure is equivalent to an algebra over this monad. And now let me make more precise what I meant. In this context, the Moré-Cartan equation, well, it's given as follows. Yes. So you see there is an infinite sum of operations appearing naturally. And you want to make sense of that. And so it happens that even in the Lie case and in the L infinity case, you need either to assume some nilpotency conditions, and that was the original framework of Getzler, or you need to complete them with respect to some filtration. So in both cases, you need some complete hypothesis. But there is an algebraic way in which you can somehow get rid of that, and it's by considering the absolute version of these L infinity algebras. And so what are those? As I said, you have a monad like this taking the sum, but in fact you have also a monad when you take the product. And so now an absolute L infinity algebra is given by a structural map like this over this monad, and then you can guess the conditions. And just to make this more precise, you can think of these operations as corollas with n inputs and one output. But here what you will have the following. So elements in here are power series of rooted trees. So in every node you think there is the corresponding ln operation. You label them by elements of G, and then what this map does for you is that it assigns to any such formal power series a well-defined image in G, without assuming an underlying topology in G, a priori. And so why did I consider these objects? So let's say all this story runs when you complete in the L infinity case or the Lie case, but when you try to generalize this story to curved L infinity algebras, it happens that even more infinite sums appear in some contexts, and you're kind of forced to consider curved absolute L infinity algebras. I will not get into the curve setting today. I just want to point out that, well, it was kind of necessary to make this generalization. And when you restrict that, so to the absolute case, what you get is that you can generalize this whole story to this setting. So you can construct an integration functor from these absolute L infinity algebras to simplicial sets. It behaves like an integration functor should. It has a left adjoint. You can generalize VCH formulas, which are already given by infinite sums to this context, and you get rational models for spaces as well. So this whole story makes sense in this context. Okay. So, yes?
If you have an absolute algebra structure on your chain code,
yes.
can you deduce from it the topology for which it is then?
Yes, there is actually a canonical topology on any such thing. And so on the algebraic level, you don't need to assume completeness with respect to this topology. But in fact, if you want to do homotopy theory, you can. It's somehow analogous to conipotent coalgebras in some sense. So in a coalgebra, you can filter by the length of the decompositions, and then you get a canonical topology. And it happens that these conipotent things are always co-complete. whereas in this setting, not always, but okay. So for the homotopy theory, you need to restrict to these complete things, but we can go back to these details after. I just want to, okay, so now what I want to do is to ask what are Lie algebras in positive characteristic. So, well, you may say, okay, well, the Lie algebras are still Lie algebras, but so in many contexts, and in particular because we're doing homotopy theory, differential graded Lie algebras no longer have a well-behaved homotopy theory in positive characteristic. So let me write this down first. So now let K be any field differential graded Lie algebras do not have, say, the right homotopy theory. And in fact, it's not even clear that you can endow them with the model structure transfer for J complexes in the first place. And so if we want to look for what could be a good analog of Lie algebras in characteristic P, we can be guided by the deformation theory story and say, okay, there's still a good, well-defined notion of an infinitesimal deformation in positive characteristic, and it happens to be encoded by some Lie-type objects. So let me be a little bit more precise, but these Lie-type objects will actually be the objects will be working in positive characteristics, so the analogs we'll be using. So, okay, let me state the following theorem by Brandner and Matthew. So there is an equivalence of infinity categories between now these formal moduli problems and something called partition Lie algebras. So now for the experts, let me just make a point. So in fact, when you define these formal moduli problems, you need to do so in terms of derived geometry, and in positive characteristic, there are somehow two versions of derived geometry which are not the same. So you can either work with spectral rings or infinity rings, or with simplicial rings. And I'll be working with the spectral version. So let me just point this out. So these will be infinitesimal deformation problems defined in terms of infinity algebras. So I don't want to get too much into the details, but just so that you know. And now I want to make the following point. So these partition Lie algebras, they were first defined as algebras over an infinity monad. So this was a homotopical statement. But then, well, I mean, if we want to do this story, and particularly if we want to replicate the algebraic side of this story, we need point set models. So, okay. Oh, now the fun begins. I guess I have to erase. Oh, it's this one? Okay. It's 3. Okay. But luckily, Brandner, Ricardo, and Jost gave some point set models for these objects. So we'll be working with those. So or at least with the absolute version of these point set models. Well, I have not been in Germany for many years. Okay, so okay, so Randall, Campos, and Newton, they gave point set models. And by that I mean a category of algebraic objects with some model structure that you can localize and get back the infinity category of partition Lie algebras. So they gave point set models for these partition Lie algebras. And so for those who know, I will make this structure a bit more explicit after, but for those who know, what you can do is so you take cobar of some infinity operad that you have linear dualized, and then you take algebras over that. And so these things will be your models. So now maybe I can state the goal of this talk. Well, generalize this story, or at least some bits of this story, to these objects. So generalize to this partition Lie algebras. So now I'm going to pick as a very specific model for this partition Lie algebras. And the reason is that for many of the proofs of the theorems that I will state, I will use the operatic calculus version that we developed with Brice-Legrignou in positive characteristic. And for that operatic calculus to work, we need to choose a priori some specific model. So, okay. So now let me be extremely naive and concrete about what I mean by a partition. And here will be the L-infinity version. So what is a partition L-infinity algebra? Well, I take a chain complex, again, and now I have operations, Ln, which are no longer symmetric, that go from G tensor n times itself to G, but now I have more operations because I have operations which are labeled by any R plus 1 tuple of permutations. Okay? And so these satisfy some relations, which I will not write down. But the point that I want to make is one way to think about them is that now you have a bracket. It's no longer Jacobi. You have some higher homotopies for the brackets. But in positive characteristic, you also need higher homotopies for the symmetries of the operations that you had before. So that's just want to give a quick intuition about what this might mean. So let me make a remark. So more concretely, these are algebras over this operad. So I take Barat-Tekel's operad, I linear dualize, and then I take cobar of that. And these are, so more concretely, these correspond to these algebras. And yeah, so why do we want that? We take this to apply the homotopical operatic calculus that we developed with Brice. So okay, so it's just a point that I wanted to make. Yes, so there is another model that Brunner, Campos, and Newton use. So maybe I can, okay, so. So the model that would correspond to Lie algebras in this setting would be taking the Lie operad and then tensoring it with the dual of a surjection cooperad that they construct in their paper. So you would still have some homotopies for the symmetries running around. Yes, but okay, so here I take Baratekos and then they take surjection. So I mean there are comparisons, it's a bit trickier, so yeah.
And do you take the linear dual? That's the causal,
No. So okay, so what happens is that the Baratekos operad is projective as an S module. When you take the linear dual, you get something injective. When you take cobar of that, it's still injective. And why is that important? Is because the infinity category of these partition Lie algebras, it does not behave like a normal infinity category of algebras of an operad. It behaves like a divided power version of such algebras. And so here, because somehow the action of the symmetric groups on this object is free, you don't see the divided power operations at the one categorical level. But this thing will compute derived invariance and not derived coinvariance. So the infinity category that you will get will still behave like a divided power infinity category. So. Now I want to say what the absolute partition in infinity algebra is. Yeah, I'm definitely getting there. So, okay. So maybe I can be more precise. So, yes. These are algebras over this monad, and now it happens that instead of the sum, I can take the product. So now let me say what an absolute partition L infinity algebra is. Well, again, the idea is that when you take the product, this is still a monad, and then you take algebras over this monad, and now what happens is a bit similar to what happened before. So here you have infinite sums of rooted trees like this. These trees are labeled by elements of G, but now on every node you have another level, which is some tuple of permutations. And so the structural morphism, gamma G, assigns to any such formal power series some image in G. And without assuming a priori some topology, even though there will be a canonical one a posteriori. Okay, so I just want to make a quick point as well. So remark. So before, if I had an absolute algebra structure, I could always restrict it to a Nel infinity algebra structure, because here I have more information. And in this context as well, if I take the formal power series, which is just the right corolla, I get back operations that satisfy the relations there. So I'll always be able to construct from one of these guys partition L infinity algebra, and this functor actually gives an adjunction. So you can always restrict such an absolute structure to a non-absolute thing, and then you get a left adjoint. Now for the remainder of the talk, what I want to explain is, well, what can be generalized to this setting?
This adjunction is one category.
Yes, yes.
So you're not talking about weak equivalences of
Yes, so I'll explain what the model structures are in a minute. And you can make this equivalent adjunction. Okay. So. Okay. So what can we generalize? So what I first want to do is to construct an integration functor for these absolute partition L-infinity algebras. And the way I will do so the idea is to consider the Barra-Teckles coalgebra structure on the cellular chains functor. So this Barra-Teckles operad is some model for infinity. You have a coalgebra structure on these guys. And the bright point about this coalgebra structure is that it's very explicit and combinatorial. And so this way you will get explicit formulas along the way for many of the things I will talk about. So once you have this coalgebra structure, and assuming you have the right operatic calculus tools to make sense of what the homotopy theory of these objects are in characteristic P, you get a triangle, commuted triangle of equivalent adjunctions, which is the following. So we have trains and it's a joint, and this will land in some category of coalgebras. I just want to make a quick point that here this operad is as cofibrant, but not cofibrant as an operad. So what I take is a resolution as an operad of this guy. And so this is what I mean by this, okay? So I can always pull back this structure to its cofibrant replacement. Now, there is a completed version of the Bar-Cobar adjunction between these things and this absolute partition L-infinity algebras. So by composing, you get an adjunction, and well, this is the adjunction I was looking for. Now I want to make homotopical sense of this thing. So on simplicial sets, you can look at the Canquilin model structure. And in fact, this object admits a model structure transfer from chain complexes. So weak equivalences of these coalgebras will be given by quasi-isomorphisms. And now what I can do is, using this adjunction, transfer the model structure to this category. And so here, I'll look at absolute partition L-infinity algebras up to these transfer equivalences, at least at the beginning. I'll talk a little bit about that after. But if I do all of this, I get a triangle of commuting equivalent adjunctions. And now let me say that this is the integration functor that I was looking for. And what I mean by that is that, well, its image will land on Can complexes, and I'll even say a little bit that it lands on algebraic kind complexes, so you have combinatorial expressions for these horn fillers, and it behaves in a way that you would expect an integration functor to behave, so I will not make that explicit now, but it behaves correctly homotopically as you would like it to some extent. Okay, so yes? Okay, so in this transfer model structure, you define weak equivalences as maps that are sent by this complete bar to quasi-isomorphisms. What you can actually show is that any filtered quasi-isomorphism, with respect to the kind of canonical filtration you get from these trees, is in particular a weak equivalence. So yeah, you can think about weak equivalences here as the 2 out of 3 completion of filtered quasi-isomorphisms.
So it's different from what you would do, like with external array with transfer from sufficient sets, which gives a slightly different a priori.
Yes. I'll go back. Yeah. give me a second. Yes. So okay. So okay. So let me make a remark. So as I said, this RG is again an algebraic kind complex, and I'll not write them down, but by looking at the horn fillers, you get higher Baker-Campbell-Hausdorff formulas, and in particular, you get, so here in this context, it's not really meaningful to say higher Baker-Campbell-Hausdorff because there was no Baker-Campbell-Hausdorff in positive characteristic. If you look at the formula, you have 1 over many things on and on and on, so the classical formula does not make sense. So here what I mean is that if you take the 2, 1 horn filler and you look at the formula, maybe this could be thought as the positive characteristic analog of the Baker-Campbell-Hausdorff formula. And then you get higher ones, which, I mean, they are hard to make explicit, but you have formulas, and, well, Annibal wrote a computer code for the Barat-Eccles operette, so eventually one can even think about putting all of this into a computer. So, well, it's not easy, but it's explicit to some extent. Okay, now let me also mention the following proposition. So now let G be a partitional infinity algebra. So I do not mean by this an absolute one, a classical one, well, classical, a partitional infinity algebra. We know they encode these deformation problems, and I didn't specify at all how you constructed an infinitesimal deformation problem out of an algebra. But what I want to state is that, well, and this is a bit vague, but so if G is homotopy complete, then you get back the formal moduli problem associated to G using this integration functor. So for the moment, you don't get all, this integration procedure does not allow one to recover all FMPs because it's defined in this absolute setting, but under some hypothesis, you can do this. And you can think of this as some kind of homotopy pronilpotency condition. So it's not that surprising either, because integration procedures in some sense are always defined with some homotopy, with some nilpotency conditions. Okay, so now I want to address the following question. Okay, can we build p-adic models using these algebras? And so it is known that somehow there is a big problem in positive characteristic, and this problem is given by the following result of Lurie, which says the following. So if I take chains, co-chains on a space with its infinity algebra structure, this is formally étal. And what it means is that somehow its bar construction is acyclic. And so the kind of models that you would like to build using some dual partition Lie coalgebras or partition Lie algebras will be acyclic. So, well, that's a big obstruction. And so it kind of means that you cannot get models up to quasi-isomorphism, but luckily, these absolute partition algebras, we consider them up to weak equivalences and not up to quasi-isomorphism. So it's not such a problem. And in fact, okay, yes. Hmm?
What are the coefficients?
Ah, yes, sorry. Yes, let me work over FP bar now. Yes. So we get the following theorem. Pointed, maybe connected as well. Important finite type space, then the unit of this adjunction is an FP equivalence. So we do get p-adic models using these partition Lie algebras. But now I want to address something that could be said about these models, which is the following. So I have chains that land on these infinity coalgebras. And, well, up to some subtlety that we'll talk about in a minute, well, we get infinity coalgebra models. And this, when I transfer this model structure, this adjunction becomes equivalent. So at the infinity categorical level, you can say that, well, both categories are essentially the same. So in some sense, these models, they are just another presentation of coalgebra models. And if you said that, well, you would be right. But now, let me make the following remark, is that the bright point about all of this is that once you have these constructions, and in particular this adjunction and this model structure, then you can do what Alexander mentioned, is that in fact, you can directly transfer the model structure from these guys into these absolute partitions. And now you get models, but in a different model structure for these partition objects. And so now they are not just coalgebra models in a sense. Okay, so yes, so let me write down this remark. So this is equivalence. So first point is that we could be happy about this being equivalence because, so recently Bachmann and Borklund constructed infinity coalgebra models for all nilpotent spaces without finite type condition. All nilpotent spaces. So one could think, okay, this would allow us to remove the finite type hypothesis on our models. The problem is that they construct this infinity categorically, and while comparing algebras of an opera up to quasi-isomorphism and their infinity analog is easy, doing the same comparison for coalgebras turns out to be extremely hard. So one can think, and I think it's true, that these coalgebras should present this infinity category, and therefore one would get models without this finite type. But, well, that's an open problem, as far as I know. And then, now the second point that I want to make is, well, you can make sure that these partitional infinity algebras do not just encode the homotopy type of coalgebras by considering, once you have constructed it, this injunction and then transferring this model structure. So this will give you a different homotopy theory on these objects, which again gives you p-adic models. Okay, so I guess I don't have much more time, so I'll try to conclude. Okay, so I'll say this and I will not write it down, but I told you that these absolute partition Lie algebras, well, because of this formally et al. Problem, they will end up being acyclic. But the fact is that you can still recover the homotopy groups of whatever you get when you integrate partitional infinity algebra from some elements in the partitional infinity algebra. So the analog theorem by Alexander in characteristic 0 is that you get them by the homology. Here it will not be the homology, it will be some elements in degree n which satisfy a condition which is more complicated. And in fact, this condition is be given by some sum of ln's vanishing, and these ln's that appear, they are exactly the coalgebra structure on the spheres. So the Baratekos coalgebra structure on the spheres, they are determined by this. So you can give explicit formulas for the homotopy groups that you get here in terms of elements of degree n which satisfy some condition up to some elements in degree n plus 1 that satisfy another condition. But these are not the homology groups. I mean, it would be very interesting to give an interpretation of these elements and what they mean, but, well, that's another question. Okay. Okay. Okay, I want to give a last application of the results here. So the application is for mapping spaces. So we get the following theorem as well. So let X be any pointed simplicial set, and let Y be a pointed, connected, nilpotent, finite type. Then the mapping space of X to the P completion of Y can be given in terms of explicit models with absolute partition algebras like this. So let me describe what's inside here. So first I start with X without any condition on X, so any finiteness condition on X, and I can look at chains on X. Now it happens that because we're working over a cofibrant operad, I can use the homotopy transfer theorem and get to the homology of X. So now we get a coalgebra which is quite small. And now between a coalgebra in an absolute algebra like this, if you look at the space of graded morphism, the vector space of graded morphism, so this will have a convolution structure. And when you integrate this convolution structure, you get the mapping space. I mean, I guess it's the pointed mapping space in this case. And so, let me point out that mapping spaces like this, well, they were studied a lot in the 80s and 90s, because if you take now x equals Cp, well, what you're doing is trying to show the Sullivan conjecture. I mean, which was proven by Miller, but also by Jean Lannes, and let me mention Lannes as well, and Schwartz, and also Lannes constructed a model for p-adic mapping spaces, but which computed the homology, and this model was given by his T-functor. So these spaces were quite studied in the 80s. And let me also mention that, well, you can also give a model in terms of cosimplicial objects, which was done by Chatour and Thomas. Okay, so maybe as a final remark, let me say that as it was talked in the previous talk, so there are curved versions of these objects, and you can actually make sense of this story in a curved setting as well. So thank you for your attention.